Alright guys, so what we want to do is just want to go through question number 5 now. I know we went through 1 to 4 last week with regards to electric circuits. Okay, we saw some examples that we see here. Okay, we did 1 to 4, and we've been practicing a lot of Ohm's law with regards to looking at series and parallel circuits. Okay, resistors, to be more specific, in series or in parallel. Okay, so on the side of question 5, okay, question 5 does mention that a battery and wires in a circuit shown have negligible resistance. Okay, calculate the current flowing through the 4 ohm resistor. Okay, so we're actually supposed to look at the circuit first to identify all the components. So we can see we have a 4 ohm resistor there. Alright, over here in series. Alright, it's along the connecting wire. Then we have another parallel circuit of resistors. Alright, a 6 ohm and a 3 ohm, an ammeter connected in series, another 2 ohm resistor in series. Alright, but with a voltmeter connected across it, and that picks up 3 volts over there. Now they want us to calculate in 5.1 the current flowing through the 4 ohm resistor. So the current that's going through that resistor over here. Okay, so how we do that? Okay, let me just get my board open. Is we need to remember the formula for Ohm's law. Okay, and we are trying to work out current, but the normal standard formulae, okay, is V is equal to I times R. Okay, that's brilliant. So just make my pen brush a little smaller and the ink flow a little higher. There you go, that should work out just fine. Okay, once we've done that, okay, we can sub in the values that we already know. So we know that there is a voltmeter value, right? So we add 3 over there, and then the current is what we're trying to work out, so that remains I for now, and the resistance was to the 4 ohm resistor. Let's just go check that out. I can't recall. Calculate through the 4 ohm resistor, so that means our resistance is of course 4. Oh no, wait, hold on. Sorry guys, I've made a little bit of an error. If I'm using the 3 volt, the 3 volt is across the 2 ohm resistor. So I have to make use of the resistance of 2 ohms. Okay, and if I divide both sides by 2, I'll get the current on the ammeter, alright, or the current that is flowing through the 2 ohm resistor to be 1.5 amps. Okay, now before you panic, okay, I'm going to conclude my answer saying that since the current is the same through the circuit, alright, so the current, the amount of current doesn't change in the circuit, okay, the current that should also flow through the 4 ohm resistor is also 1.5 amps, okay. So in our final answer, therefore, since the current in the circuit remains the same, okay, remains the same, the current through the 4 ohm resistor is also 1.5 amperes, alright, or just amps. On to 5.2, they want us now to calculate the current flowing through the 6 ohm resistor. Alright, now the 6 ohm resistor is the resistor that is connected in parallel. Okay, so here's what we're going to do. First we're going to do is we're going to calculate what is the parallel resistance. Okay, so let's go here. Let's see, you have space here. Okay, no, that was at the top. Okay, great. So let's go to 5.2. Okay, so we're first going to calculate parallel resistance. So 1 over R parallel is equal to 1 over R1 plus 1 over R2 equals 1 over 6 plus 1 over 3.
1 over 3.
Mm-hmm.
Yeah.
And then
that is equal to 3 over 6.
Uh-huh. Which is
and then that would equal to 2 ohms because you flipped over.
Exactly.
You're
Okay.
You're not flip it over?
No, you're going to.
Or
I'm just what I did was if you had to do this, type this section here on your calculator, it wouldn't give you 3 over 6, it'll give you 1 over 2. So 3 over 6 is the same as 1 over 2. Alright, obviously still for 1 over R parallel, but therefore you flip it over, which is the mathematical terms, the reciprocal, it becomes 2 ohms. So you are 100% right there, Mr. Ravens. No room for error there. Lovely. Okay, cool. Now, one part of the question is done. It's about 3 parts. Okay, cool. Remember that the question is asking us to calculate the current flowing through the 6 ohm resistor. That's still the main objective. Okay, now we have the resistance already. We need to find out what is the voltage that's going through this parallel circuit, because remember it's going to be the same. So we're moving on now to the voltage that's across the parallel circuit is equal to the current times the resistance. Okay, now the current in the circuit is 1.5 amps multiplied to the resistance of the parallel side of the resistors is 2 ohms. So therefore the parallel voltage, or the voltage that's across the parallel part of the circuit, is reading 3 volts. Right? Therefore, last section is now we can use again V is equal to I times R. We know the voltage is now 3. Okay. We know that the current is what we're trying to find out, and the resistor that we're concerned with is the 6 ohm resistor. Okay, so now we have to divide both sides by 6, and therefore the current that is only going through the 6 ohm resistor is equal to 0.5 amps. So that means that if that's 0.5 amps going through the 6 ohm resistor, then 1 amp is going through the 3 ohm resistor, because parallel, remember, the current splits. Okay, it's got 2 ways to go instead of just 1 way. Okay, so it can split itself up. Okay, and obviously in this case it hasn't split up or split itself up equally. Alright, for 5.3 though, calculate the potential difference that is across the battery. Okay, so the battery basically represents the total voltage or potential difference within a circuit. Okay, so we're going to use the formula called VT. Alright, the total voltage. It can only come from the battery, because that's the total supply of volts for the entire circuit. That's equal to the current that's in the circuit, alright, multiplied by the total resistance that's in the circuit. Okay, the total resistance of the circuit is quite easy to calculate. We know there was a 2 ohm resistor. We know the parallel resistance was equal to 2, and we also know that the other resistor in series was equal to 4 ohms. Therefore, the total resistance in the circuit that's present there is 8 ohms. Okay, wonderful. So what do we do in order to calculate the total voltage that's in the entire circuit? Okay, what we do, we take the current, which is 1.5, multiplied by 8 ohms, which is the total resistance, to get total voltage. Therefore, the total voltage that's being supplied by the battery is 12 volts. Alright, and we should have all got that one. And then 5.4, unfortunately I can't scroll any further down here, guys, but I am able to read off what is going on here, what's the final part of that question. 5.4 asks us to calculate the current flowing through the ammeter if the 6 ohm resistor is removed. If the 6 ohm resistor is now removed, obviously we have kind of decreased the resistance. Have we? No. We've actually not decreased the resistance. In fact, we've increased the resistance. Let me show you why. So remember this parallel resistance over here, right, consisted of a 6 ohm resistor as well as a 3 ohm resistor, right? If we remove the 6 ohm resistor, we take it out and we keep the 3 ohm, okay? The 3 ohm resistor now moves into series with the 4 and the 2 ohm. Right, let me flip back. Can we see that? If we take him out, that means that 4 ohm resistor is in series now to the 3 ohm resistor and is in series to the 2 ohm resistor. Because if you remove one of the parallel components, it's no longer parallel. It becomes series. Now we need to calculate the current that's flowing through the ammeter if the 6 ohm resistor is removed. So if the 6 ohm resistor is removed, let's check RT now. Okay, that means we still have the 2 ohm resistor, we still have the 4 ohm resistor, and now we only have the 3 ohm resistor. So let's count here. Well, 4 plus 2 is 6, plus 3 is actually 9 ohms. So we've actually increased the resistance of the circuit now. It was, total resistance was 8. Now total resistance, now that the 6 ohm resistor is gone out of the circuit, is now 9 ohms. So let's check now. What is the, sorry, this is new RT, okay? We put in brackets, this is new. So now let's check what is going to be the current flowing through the ammeter now. If the resistance is increased, I wonder what's going to happen to the current. Let's check. Vt is equal to I times RT. Okay, we know now that the battery is supplying 12 volts, so that now it still doesn't change. 12 volts is equal to the current times the 9 ohms of resistance in the circuit. We divide both sides by 9. Okay, that's a very weird 9. It looked more like a G there. Let me fix that. There we go. And here as well. There we go. Alright. So 12 now divided by 9. Okay, let's see what we get there. Therefore, current, or I, is going to equal, okay, well, what's 12? 3 is divisible by all of them, so that's 4. Alright, and that's 3, so we get 4 over 3. 4 over 3 in decimal is 1,33 amps. Okay, so current in fact has decreased from 1.5 and is now decreased to 1,33 amps. Alright, electrical power, like I mentioned this to you last week and just a few moments ago, is that this is the final section of electric circuits. Yay, almost done. Okay, and we're going to learn also about what energy has to do with power in this section. This one is quite fun, and fun. Last section is not as intricate as your electric circuits. These calculations can be a bit more simpler, alright, but you must also watch out with anything, alright, if you don't have, just like a warrior or soldier, if he doesn't have all his weapons, alright, he becomes a bit of a disadvantaged, or more disadvantaged than the enemy. Okay, so you need to make sure we still know all that we need to know about circuits. We take our knowledge over because we may be required to solve an electrical power question, but first few steps that we need to do is solve the electric circuit question, part of the question. Alright, and they will all follow on almost like a flight of stairs spiraling down from an upper level to a lower level. Great. So, what is power? What is the definition for power? Okay, power is a measure of how rapidly work is done, or power is a measure, alright, of work done. Alright, and it can be looked at as the rate at which work is done, or per unit time. Okay, and power is measured in watts. Alright, or watt. Why 1 watt, right, or 10 watts, okay, well, not 10 watt, 10 watts, okay, it's measured in watts, which is, that's a capital W, okay, which is the same as joules per second. So 1 joule per second is the same as 1 watt, okay, W-A-T-T, Okay, now we can calculate electrical power. Now, electrical power is slightly different. Okay, in electric circuits, power is a function of both voltage and the current. Okay, so when we talk about power that is being dissipated, okay, in an electric element, we are looking at P is equal to I times V. With that being said, electrical power is the rate at which electrical energy is converted in an electric circuit. Okay, and the calculation as we see there is P is equal to I times V. Alright, where power is P, which will be exactly equal to current, which is I multiplied by the voltage. Okay, another thing that we need to mention there is there's no extra constant of proportionality. Right, in other words, that is the only two elements or factors of that we need to consider when calculating electrical power, the current and the voltage. And of course, I've mentioned the measurement of that is in watts. Now, P is equal to I times V is great, it's all wonderful, but there are some equivalent forms. So sometimes the question is not as simple. Of course, everything starts out very simple when it comes to any type of new concept in physics or even in the subject of mathematics. Physics and mathematics are very closely linked, of course. Okay, so we can use Ohm's law also to show that P is equal to I times V, or V times I, is the same as saying power is also equal to the current squared multiplied by the resistance, or the squared velocity, the squared voltage, sorry. I saw V and my brain instantly switched to velocity. Or the squared voltage divided by the resistance. Okay? So we can actually prove using Ohm's law that we can actually form two new equations based on P is equal to I times V. So, if we have a look there, if we use V is equal to I times R, let me rather explain it to you this way. Okay, let me just pick another board here. There we go. All right. So we have the first power formula, right, which is P is equal to V times I. Okay, some textbooks write it I times V. Doesn't matter. V times I is the same as I times V. Okay, doesn't matter which way you write them. But we have two other equivalents, like I've mentioned already. Okay, and a couple of these equivalents then do include the following. So if I take P is equal to V times I, right, for Ohm's law, okay, for Ohm's law, V is equal to I times R. Alright, we remember that, we just did it. Do I see a comparison here? Yes, I do. So I can technically, if I know that the voltage is equal to the current times the resistance, and now I need to take the voltage times the current, what happens if I don't have a voltage, but I have current and I do have resistance? I can form a new power formula to say, well, therefore, P should be equal to I times R, which is in place of V, times I, which will equal another power formula of I squared times R. And I formed an entire new formula, factoring Ohm's law into the power equation, which I can because since power harbors and inherits and also adopts two elements or factors of Ohm's law, which is namely current and voltage. Okay, now let's have a look at the third one. The third one, remember I've still got P is equal to V times I. Okay, now let's look at the third one with regards to the fact that what happens if I use Ohm's law formula that, sorry, let me make this colon and not equal, that I is equal to V over R. Alright, I is equal to V over R, the voltage divided by the resistance. Let's check who's here. Hello, Danae. All right, welcome.
Hello.
All right, welcome. Just pick up where we just left off. Okay, we are doing electrical power, and I'm just explaining the formulae. So you can go ahead and take these down for electrical power. I'll actually put the heading here, electrical power. There we go. Alright, so I use the Ohm's law. I is equal to V over R. Therefore, I can form a third power formula saying that P is in fact equal to, if I keep, let me just see, if I keep, so I keep V as normal, but I sub in V over R for I. So I sub in V over R for I times V. Alright, so if it's V times V, it doesn't matter. It'll form an entire new formula saying that P is actually equal to V squared all over R. So the voltage squared all over the resistance. So here the C.R. Vula textbook has some wonderfully worked examples through which we can have a look and see how electrical power should be calculated. Okay, so we have work example 8 for electrical power. So the question is, given a circuit component that has a voltage of 5 volts and a resistance of 2 ohms, what is the power dissipated? Right, so step one, first thing that we need to do is we need to write down what we have been given. Okay, this is what I always do as well when solving a question and writing out what I don't have. So they do it the same way. So they're noting that I have a voltage of 5 volts, V equals to 5 volts, R is equal to 2 ohms, and the power dissipated, well, that's what I need to find out. Okay, notice I only have, alright, I only have V squared, I only have voltage, and I only have resistance. So I only have voltage and I only have resistance. Right, I only have those two. So I need to go pick a power formula that only has those two. Alright, so I haven't been given any current, so I can't use this formula, which is the initial formula that they give us. I can't use this one either, I squared R, I can't use that. I have to use the V squared over R formula. Power is equal to the voltage squared divided by the resistance. Okay, so the equation for power, okay, they seem to have incorrectly stated it here in the textbook, but it's fine because they corrected here. So the correct formula for or equation for the power calculation is P is equal to V squared over R. We sub in 5 for voltage, we get 5 squared divided by 2, which we sub in for the resistance, and we get the final answer of the power to be equal to 12.5 watts. Right, very important. Let's have a look through worked example 9, which is also an electrical power question. Alright, here we only have a battery, alright, and we only have a resistor. That's our circuit. The resistance of the resistor is 15 ohms, and the current going through the resistor is 4 amps. Okay, they would have had to somehow have calculated that. Now they want to know what is the power for the resistor. The same thing as what is the power dissipated. It's the same thing. Okay, so they've given us a current and they've given us a resistance. So now we can go use the formula for power where P is equal to I squared R. Okay, because we have current and we have resistance. Okay, so we sub in 4 amps for the current, so we end up with 4 squared multiplied by 15, which is the resistor, which we subbed in for R. So 4 squared times 15, therefore the power for the resistor, or the power dissipated, is 240 watts. Okay, great, nice, easy example here. Now example is going to get a little bit more intricate. Alright, so let's have a look here at the 10th example, which has a little bit more of a jungle gym setup for us, right? Much more things that we can play on. Okay, so this question is power in series. Okay, so we have two ohmic resistors, which is R1 and R2. R2 doesn't seem to have a value yet, but we know the value for R1. They are connected with a cell. Okay, find the resistance and power of R2 given that the current flowing through R1 and R2 is 0.25 amps, so that means that's the current in the circuit, and that the voltage across the cell is 6 volts, and R1 is equal to 1 ohm. Okay, so the solution could be to draw the circuit. Thank you very much for drawing it for us, Siyavula. Okay, cool, fantastic. So now we've identified that there is a 6 volts or potential difference across the cell. There is a current in the circuit of 0.25 amps. There is a resistance of 1 ohm for R1 and a resistance unknown for R2. Okay, and we need to calculate or find the resistance and power of R2. So you see how they first using Ohm's law in the question, because in Ohm's law says we first need to find the resistance. Now we can use it with Ohm's law. Yes, we can. Okay, we can check if we can use it with the power formula, but if they're asking us to calculate both, we can't do both at the same time because resistance forms part of the power formulae. So we can't find both or look for both using the power formula. We need to go do one thing first and then the other. Okay, so let's determine how we're going to approach this question. Like I mentioned, you need to use Ohm's law. To first calculate what is the total resistance in the circuit. Okay, and then you can calculate the unknown resistance using R is equal to R1 plus R2. Okay, so we first need to find what is the total resistance in the circuit, and then we can go use the R or RT is equal to R1 plus R2. We know the value for R1, that we can do a calculation and solve for R2. So let's find total resistance first. Total resistance in the circuit, we know because we have the total voltage and we have the total current, we can find total resistance. So resistance is going to equal to V over I. Total voltage was 6, total current was 0.25. 6 divided by 0.25 equals to 24 ohms. Lovely. So 24 ohms is the total resistance in the circuit. So we now know what the total resistance is, and we also now know, or we knew rather, what was the value of R1, which was 1 ohm. So if I solve with R is equal to R1 plus R2, if I solve for R2, I'll get the value of R2 to equal 23 ohms. Alright, now I can solve the problem because now I found the resistance of R2, and now I can calculate what on earth is the power that's going through R2. Okay, so P is equal now to I squared times R, because I have the current going through it. So 0.25 squared times 23, which is the resistance of R2, I get 1.44 watts. And I state it publicly or academically or neatly at the bottom there that the power for the resistor R2 is 1.44 watts. Alright, work example 11. Now, previous example, like I mentioned, we did work through power in series, but now what happens when we are given series and parallel components? Okay, so you see there we have R1 in parallel to R2, and we also see in parallel circuit 2 we have R3 in parallel to R4. So parallel circuit 1 would be R parallel 1, so whatever value we get there will be the value for R parallel 1 once we work out the parallel resistance. If we work out the parallel resistance for the parallel circuit 2, obviously that number will represent RP2, which is the parallel resistance for circuit 2. Okay, we are given the following circuit and also the following questions. Okay, so we've all seen the circuit. Let's go have a look at the questions. So the current leaving the battery, let's go find where the battery, okay, there's the battery. The current that's leaving the battery is 1.07 amps. The total power dissipated in the circuit is 6.42 watts. the ratio of the total resistances of the two parallel networks, RP1 to RP2, is 1:2. The ratio of R1 to R2 is 3:5, and R3 is 7 ohms. Okay. Already, without even looking at the question, a couple of people might be a bit mind confuzzled. Right? We never panic. We relax. What have we been given? We know the total power. We know that the total resistances, so the value for RP1 and the value for RP2 technically is there. It's just hidden in a ratio. Because that means that 1:2, that means that RP2 must be double that of RP1. So the values are there, it's been given, it's just hidden. It's given at the same time it's hidden. Okay, it's like a treasure hunt. If you go to a certain place to for a treasure hunt or Easter egg hunt, they've technically given the Easter eggs to you, they've just hidden it from you. Because you're at the place where it is. They've given it to you. But just go find it. Okay? They also mentioned that the ratio of R1 to R2 is 3:5. Okay, now you can simplify 3:5, okay, of the individual resistances, R1 and R2. They've given us a value for R3 though. R3's value is 7 ohms. First, they tell us to first calculate the voltage of the battery, then the power dissipated in R1, RP1 and in RP2, and then the value of each resistor and the power dissipated in each of them. My gosh! Alright, seems like a load. Okay, let's take it one step at a time. Step 1. What is required? Okay, well, we need to first make sense of the question. That this question, they've actually given us various pieces of information and asked to determine what? The power dissipated in each resistor and also in each combination of resistors. So power in each individual resistor and also the power in the combination of the two of them, of each pair. Notice that the information given is mostly for the overall circuit. Okay, so they tell us the power that dissipated in the entire circuit. The current as well. Okay, we can use this, we can take this as a clue, and we can start with the overall circuit, and then we can break it down and work our way towards the individual components. Okay, so let's do that. Let's start with step 2 quickly, with calculating the voltage of a battery. Okay, so firstly, we need to focus on the battery. Like I mentioned, we are given the power of the overall circuit as well as the current that is leaving the battery. So now we can use the formula P is equal to V times I. Because we have now the total power and we have also the current that's leaving the battery. So if the current leaves the battery, that means that's the current in the circuit. Okay? So let's go calculate that. So now P is equal to V times I. We rearrange the formula to solve for V. Alright, so 6,42 divided by 1,07 gives us 6 volts. That means that is the voltage that is across the battery. Okay, we are happy. We have our voltage across the battery. We can carry on working down now to the other individual components of the circuit. The next part of the question did ask us to go through and find the power that was dissipated in the parallel component 1 and the parallel component of 2. So there was RP1 and RP2. Okay, so remember that when we're working with the overall circuit details, okay, we need to work our way down towards those individual elements like I've mentioned. So we treat the parallel networks as if they are equivalent resistors. Okay, we treat them. So that's why we kind of drawn it to look like this. Okay, that when we get what's the value for the parallel circuit, we treat them as one resistor. Almost. Okay. So, carrying on with the question, we know that the current through the two circuit elements will be the same because it is a series circuit, and that the resistance for the total circuit must be RT is equal to the parallel component of the RP1 plus RP2. We can determine the total resistance again by using the Ohm's law. Okay, so we have the voltage of a battery as well as we have the current. So we can actually, because we have the total current and because we have the total voltage of the battery, which is the total voltage of the circuit, I can now find the total resistance once again. Okay, so we have 6 volts divided by 1,07 amps, and then we have 5,67 ohms to be our total resistance still in the circuit. Great. Now that we got a total, now that we got a total volts, we've calculated the total voltage of the battery, we have total current, we have total power, and now we also have total resistance. Okay, so we're on our way to calculating each individual component. Right. We know that the ratio between RP1 to RP2 is 1:2. Okay, we know that. Okay, which means that therefore RP1, alright, must be half that of RP2. Alright, and the total resistance must be equal to RP1, which is parallel, the parallel resistance 1 plus the parallel resistance 2. Okay, so if RP1 is equal to half that of RP2, alright, because RP2 is double that. Okay, 1:2. RP is twice that of 1. So RP1 is half that of RP2. Okay, because 1:2 is basically the same as this fraction over here. I can sub in half RP2 for RP1. So I have RP1 plus, I have RP2 plus RP2, or half RP2 plus RP2, sorry. That gives me 3/2 RP2. Now I can sub in my value for the total resistance, which is 5,61. Okay, I can divide both sides, or I can times both sides by 2 to get rid of the fraction, and then divide both sides by 3. Okay, and basically I'll end up with 2/3 times 5,61. I'll get the value of RP2 to be 3,74 ohms. Okay, there's a lot of ways now that I can do this. I can calculate RP1 in multiple ways, since I have the value for RP2 and let me just do it here. This is a new, just draw a line side here, because this is a totally new frame. Okay, so since RT was equal to RP1 plus RP2, and I knew that was 5,61, and I know that equaled to RP1 plus, I just worked out now, 3,74. So therefore RP1 must equal to 5,61 minus 3,74. Okay, and then therefore RP1 should equal, let me just check where's my calculator. I always got to make sure, of our answers, no matter how good my brain is. Okay, 5,61 minus 3,74, and I still get the same answer that the textbook gives us, which is 1,87 ohms. Okay, let's have a look, and yes, it is. Okay, so what they did, the textbook did, they just subbed the value of RP2 in this equation over here. RP1 is equal to half that of RP2. As we can see that it's less work, okay, because it's just half that of 3,74, and we get the value. But you could have also subbed it into the RT equals RP1 plus RP2. You will still have got you the same answer. I just did the alternative because I like to be different. Right, there we go. Now that we also know that the total resistance of each of the parallel networks, we can now calculate the power dissipated in each of them. Okay, So we use the power that's dissipated in the parallel network, or the first parallel network. So P1 is equal to I squared times RP1. Okay, notice that we use the parallel network value. So the value of R parallel in the first parallel network is 1,87 ohms. The current stays the same throughout the circuit. So 1,07 all squared multiplied by 1,87 gives us the power across the first parallel component or network to be 2,14 watts. We do the same thing with the second network, just sub in a different value, and we find out the power dissipated across the second parallel network is 4,28 watts. Quite simple to understand so far, I feel. Now let's work out the fourth step, okay, which is looking at the parallel network 1 combinations or calculations. Okay, what can we now begin to do? We can now begin to find the detailed calculation and have a look at the resistors in each of the parallel components. Okay, but let's look at the first set first. Okay, we now know that the resistors or the resistance for R parallel 1, okay, is 1,87. Alright, we calculated what it was for R2 to be 3,74, and the parallel resistance to be this was for RP2, and the parallel resistance of RP1 to be 1,87 ohms. That's great. But remember, they gave us a ratio. So they said that we know that the ratio between R1 to R2 is 3:5. Okay? This means that we know that R1, alright, is 3 over 5. I was going to say 3/5. Yeah, 3/5 is correct. 3/5 that of R2. Okay, because 3:5, that basically is 3 over 5. The ratio is the same as a fraction, expressed differently. So, we also know that the total resistance for the two parallel resistors in this network, like I mentioned, is 1,87 ohms. Okay, so let's use the relationship that we have now between these two to find out the individual resistors. Alright, so 1 over RP1 is equal to 1 over R1 times 1 plus 1 over R2. Okay, so we know that R1 is equal, alright, R1 is equal to 3/5 R2. Okay, if we sub that in, so we have 1 over R parallel 1, or 1 over RP1 is equal to 5 over 3 R2 plus 1 over R2. And I will explain the reasoning for this. Alright, so 1 over R1, and you might be asking, why is R1 equal to, if R1 was equal to 3 over 5 R2, why isn't it 1 over 3 over 5 R2 here? And the reason being is for this exact reason. If we have 3 over 5, R1 is equal to 3 over 5, or 3/5 that of R2. If we flip these into the parallel equation, we have 1 over R1 is equal to 1 over 3/5 R2, or 3 over 5 times R2. Okay, this first part over here is basically saying 1 over 3 over 5. 1 over 3 over 5 is the same as 1 divided by 3 over 5, or 1 divided by 3/5, which changes to 1 times 5 over 3, and then we get 5 over 3 times R1, and R1 was already the denominator here, so we just get 5 over 3 R2, okay, which is present in the textbook over here. So we have 5 over 3 R2 plus 1 over R2. Okay, 1 over R2 is definitely the common factor, so take it out, and we end up with 5 over 3 plus 1, which is the same as saying 5 over 3 plus 3 over 3. Alright, because 3 over 3 is equal to 1, and our other denominator here is over 3, so we know it's 3 over 3. If we do that, alright, and we multiply them, or we add them together, we get 8 over 3, an improper fraction. So 1 over R2 multiplied by 8 over 3, or 8 over 3 R2 if you wish. Alright, then what do? We need to flip this over. Okay, If we flip that over, we'll get RP1 is equal to RP2 times 8 over 3. Okay, and we are trying to find the value for R2. Okay, so R2 is basically equal to RP1 times 8 over 3. We know what the value of RP1 was equal to, 1,87. We're still multiplying that by 8 over 3, and we get the value of R2 to be 4,99 ohms. Once we get that value of 4,99 ohms, we can also calculate what R1 is. Okay, R1 is basically equal to 3 over 5 R2. We know what R2 is, the value for it. We just sub it in, so 3 over 5 times 4,99. Value of R1 is equal to 2,99 ohms. And now we want to calculate what was the voltage that was across that parallel component of the circuit. Okay, the total voltage going across each and every one of them. Okay, which is V is equal to I times R. You know, current in the circuit was 1,07 times the parallel resistance, which was 1,87, and we get 2 volts. So that is the parallel voltage. Okay, now that we have the parallel voltage, which is the voltage across both of those resistors, we can calculate the power that is power going through each of those resistors individually. So P1, all right, which is the power going through the first resistor, which is R1. So we know the voltage across it is 2 volts, so it becomes 2 squared divided by 2,99, and we get a value of 1,34 watts. And then we do the same thing, but for the second resistor, R2, using its resistance of 4,99, we get a value of 0,80 watts. And then the same thing would occur for these parallel network 2 calculations. Okay, the difference here is that they told us what was the value of R3, okay, but they also gave us a ratio, I think, for this one as well. So R3 was given to be 7 ohms, okay. We know what RP2 was equal to, okay, so now we can calculate what was the value of R4. So we calculated that RP2 was 3,74 ohms. So what we do is we take, well, 1 over RP2 is equal to 1 over R3 plus 1 over R4, while 1 over 3,74 is equal to 1 over 7 plus 1 over R4. So we can first solve the fractions. So 1 over 3,74 minus 1 over 7, and then we can flip our answer around there to get the value of what R4 is equal to, which is equal to 8,03 ohms. Quite basic, this one. Okay, this is a little easier than working out the values of the resistors in the first parallel network. And now lastly, what we're going to do is now we want to calculate what is the voltage or the parallel voltage going through each of the, or going through the parallel components, parallel network number 2. There's an easier way to do that, people. I know we have the resistors of each, okay, but we know the total voltage that was in the circuit, right? We also know the total current, but we also know what was the parallel voltage across the first parallel network. That was 2, and the total voltage is 6. All right. So if 2 volts was measured across the first parallel network, the difference is measured across the second. So 6 minus 2. We get 4 volts. So the parallel voltage going across the second parallel network is in fact 4 volts. Now that we have that, we do the same thing. We calculate the power dissipated in each resistor. P3, V squared over R3. So 4 squared divided by 7 gives us 2,29 watts. And for the fourth resistor, we have 4 squared divided by 8,03. We get 1,99 watts. What we're doing now is we're going to have a look at this exercise 11.6. We're going to have a look at the question 1 to 4. Okay, question 1, which we see over there in the Siavula textbook. Okay, let me just go a little, focus a little down, just like that. There's B as well. Okay, so we're going to do up to 4A up just for now. Okay, which is question 1. What is the power of a 1 times 10 to the power of 8 volt lightning bolt having a current of 2 times 10 to the power of 4 amps. Just want to know the power there. So this question starts off quite basic, and we'll see how far we get Okay, but this is the little bit of end of the lesson activity that I'd like you to just go through, please. Right, everyone, I just want to take you all through just a few, maybe 2 examples, okay, of the questions that I just put up for everybody. Okay, so I'll do the first two, alright, and see how far we can get. Okay, so if I do the first one, this example, or exercise 11.6 in the Siavula textbook. Okay, and the first one they asked us for, if I just look at the question again, what power, or what is the power of a 1 times 10 to the power of 8 volt lightning bolt having a current of 2 times 10 to the power of 4 amps? How do we do that? Well, this is the simple basic power formula of P is equal to V times I, or I times V. Right, the volts was 1 times 10 to the power of 8. I'm going to use brackets for neatness, times 2 times 10 to the 4 amps was the current, and therefore the power that I'm going to get out of this lightning bolt was 2 times 10 to the 2 watts. Okay, that was pretty basic, pretty easy. Okay, do number 2, next to it. They asked us here for number 2, how many watts does a torch that has 6 times 10 to the 2 coulombs passing through it in 0.50 hours, alright, use if its voltage is 3 volts? Alright, so that's how much coulomb pass it in half an hour. 0.5 is half an hour. Alright, 1 hour would be 1, alright, but it's decimal. 0.5. If they were telling us that was the time, that it would have been 0 colon, right, or 00 colon if it was at a specific time. Okay, but it's 0.50 which means half an hour. So we obviously need to convert that to seconds. Okay, so how I understood that question was they told me that the voltage was equal to 3 volts, or 3.00 volts. They told me that the charge was equal to 6.00 times 10 to the power of 2 coulombs. That was the charge. They told me that the time, or delta T, was equal to 0.5, which was half an hour, okay, which is 30 minutes, which is equal to 1,800 seconds. Okay, remember it's a torch, eh? So makes sense. So now first thing we need to do is we need to use the coulombs, or the charge formula, to calculate the current. The Q is equal to I times delta T, grade 10 formula. Okay, and is present on the formula sheet as well. Okay, so we know the charge was 6 times 10 to the power of 2. It's equal to the unknown current of I times 1,800. Okay, divide both sides by 1,800. Okay, therefore we get the current to equal 1/3, right, amperes, or which is also equal to 0.33 amps. Now that we have that, we can now use the power formula. P is equal to I times V, because we have the voltage. So P is equal to I times V. We have 0.33, right? Then we multiply that by 3. Therefore, the power that's going through this torch is 1 watt. Sorry, that must be capital W. 1 watt. I'm sure we all got that. Alright, and that is all we have time for in today's recording, so that's where we will leave it there. So thank you all for joining me on electrical power. Next week we do electrical energy.